here, and so happy that you guys can be here. As you know, this live show is all based off of your guys' questions, all of your tweets that you tweet me throughout the week, and I already looking at the chat, and goodness, you guys are all here. This is probably a packed live compared to most of the typical lives. Where have you guys been all semester? But happy to see you guys are here. I want to give a shout out to everyone that's here. I'm going to quickly read off names. We have Amy, we have Nathan, Jade, Krista, Eliana, Morgan, Ruben, Kaylee, Jade, and then Divya. So thank you so much for being here. This comment is hilarious. Queen, where you at? I'm right here. So happy you guys can make it. I am going to be going over several different topics. These are based off of multiple tweets that I was getting throughout the week. And actually, a lot of you guys had the same questions. You wanted me to go over lattice structures, unit cells, and I got like multiple questions on that and even emails on it. And then I also got people saying intermolecular forces. Multiple people were asking for that. So perfect. I'm glad that I could answer a lot of people's questions. And someone just said, do biology. I was a chem major, didn't see much bio. So sorry, don't really have much experience there. But chemistry, that's what I have down. All right. So we're going to start off with intermolecular forces, and before I start going into all of these different types of topics, really, that I know are going to help you with your finals, because I can see that people have finals this coming week, right? So I know that that's the typical thing here, is you guys are going to have finals. I see on Tuesday, on Friday. I have other students that I've seen on Thursday. So we're going to get going on this. Also, if you guys could give this video a like if you enjoy these live sessions and if this helps you out overall. So make sure to give this video a like. And then another thing that I wanted to mention, Jade mentioned the chemistry survival guide is free and helpful. Happy to hear. And if you haven't downloaded your free chemistry survival guide, make sure to do that. It's in the description box of this video. So go ahead and do that. That's going to help you so much with preparing for finals, for really anything. It even has general chemistry 1 and 2 if you're continuing on to the second half for the following semester. So that's all there. Another thing is there's even more resources that I have in the description box. Towards the bottom, what you're going to find is specifically a link that goes out to Chegg Study. And that was a huge lifesaver for myself. So as you guys know, I was a chemistry major in college. And a chemistry major doesn't just take chemistry classes. You take so much math and so much physics, or at least a year of physics. So I had to take multiple chemistry classes, physics classes, and calculus classes. So luckily Chegg was able to help me out there, because a lot of times I didn't understand my homework. And what it is, Chegg Study is just a way to help guide you through your homework. So it's like a solution manual in a sense, but how you want to use it is if you're stuck on your homework question and you have no idea what you're doing, that luckily lists it step by step. It's a step-by-step solution. And then from there, you can tell, oh, that's what was tripping me up. Oh, that was where I was, making a mistake. So I highly recommend checking it out. The link is in the description. And as a disclaimer, if you do decide to go with Chegg Study and purchase it, then I do get a small commission. I am part of their affiliate program. Where that goes, it just goes to making more videos for you guys, as I'm always making more videos. Another thing I wanted to mention was today actually is the last day that I have a sale on all of my notes. They are currently 40% off. I've never gone that high before. So for finals, all the notes, like everything that I have currently on my notes are 40% off. That is a huge sale. So it ends today, at the end of today, but make sure to get that before the sale is done. So I just put the link in the chat. And if you guys don't know, the notes that I create are a simplified version of your textbook. So it's a lot shorter, and it's basically just everything that you need for that specific topic to pass a test on that topic. So make sure to check that out. Okay. Let's jump right in, guys, to intermolecular forces, see what they are and what types we have. So intermolecular forces are going to be the forces between molecules. All right, so when we're talking about molecules, you're going to see it's going to be like 2 or more molecules. So like something like this, where they're really just the forces between them, and it's represented by this pink sort of dashed line, where these two are intermolecular forces, it's those two that are kind of attracted to each other. Now, that's different from intramolecular forces. So intramolecular forces is actually just talking about that one molecule and just the bond in between those two atoms of that molecule. It's not saying there are two or more molecules, it's just saying really there's only one. So that's the difference between intra versus intermolecular. Okay, so that's what I want you guys to know. That is a good multiple choice question for a final. So for finals, I definitely see intermolecular forces being on there. This most likely is going to be on your multiple choice section if you have a multiple choice section. And then let's go over the strongest intermolecular force that you're going to see and the weakest. And then we'll figure out how you can just tell which one's which. And then, of course, we're going to go over the trends. So like, how does intermolecular forces affect vapor pressure or boiling point or, viscosity or something like that. So the first one that we're going to see is called ion dipole. So ion dipole is going to be our strongest one. And then I'll go over every single one, so don't worry. I'll go over what everything means. I'll give you an example, and it's going to be really helpful. So then the next one is going to be hydrogen bonding. So it starts off with ion dipole. That one's not as common. The one that's going to be more commonly seen, I'd say, is hydrogen bonding as your strongest, but I'll still go over it. And then the next one is going to be dipole-dipole, and the lowest, the absolute weakest, is going to be London dispersion. So as I mentioned, the weakest is London dispersion, and the strongest is ion dipole. And this is just how it ranges for our intermolecular forces. It goes down in the strength. Okay. So now let's start with just our first type, the ion dipole. And then in this case, ion dipole is referring to an ion. And remember, guys, what an ion is. An ion is just an element with a charge. So we can refer to it as being a cation. So a cation, it just means it has a positive charge. It's an element with a positive charge. An anion is a negative charge. So an anion is an element with a negative charge. So in this case, if I were to have, let's say, Na+, then I know this is my type of ion or cation. And what's happening with ion dipole is an ion, so Na+, is interacting with a polar molecule, which is water in this case. And what I want to remind you guys of what a polar molecule is and how we know something is polar. So when we're talking about polarity, we're talking about an unequal pool of electrons. So like that little movement that I just did, I want you to think of it like a tug of war between elements. So thinking of that, if I were to look at, if I were to just look at oxygen versus hydrogen, and if I were to look at the periodic table and see, okay, well, which one's the most electronegative, because that's how we can tell which one's stronger. Whatever is closest to fluorine, remember, is going to be the most electronegative atom. So oxygen on our periodic table is closer to fluorine versus hydrogen, which is on the complete opposite side of the periodic table. So I know oxygen must be stronger or more electronegative. That means that it's going to pull in that direction. So it does have that unequal pool of electrons. If we were to look at another factor for polarity, we know it's polar because there are lone pairs. The fact that there are lone pairs on our central atom, that kind of adds to making it even more polar because it's adding more electrons on that atom. So it's once again having that unequal pool of electrons. So that's another thing, by the way, when you do have like Lewis structures and you aren't too sure, is this polar, is this nonpolar? First, start off with saying, is it symmetrical? If it is, then it's nonpolar. Next, look at, do we have that unequal pool of electrons? Are there lone pairs on that central atom? If there are lone pairs on the central atom, then yes, it is polar. So that's how I can instantly tell with this that, yep, this has to be polar. So the fact that I know that this is polar and that this is my ion, and that interaction is our ion dipole. I just got a question from Krista Joy saying, what about ion-induced dipole and dipole-induced dipole? Those were confusing me. So yeah. So that's what we're covering right now. So this first one is the ion-induced dipole. And then the third one that we're going to go over is dipole-dipole. So the first one, ion-induced dipole, is really just talking about we have an ion, so something that's charged, and it's interacting with a polar molecule. So that's how we know. All right, this next one. So this next one, I know a lot's going on the screen, but what I want you to know for this one is hydrogen bonding. Hydrogen bonding can be a little bit tricky at times, so let's make sure we get this down. With hydrogen bonding, essentially what we're looking for is we're looking for the bonding or like forming a bond between hydrogen and fluorine, or hydrogen and oxygen, or hydrogen and nitrogen. So the main atoms that you're going to be seeing are fluorine, oxygen, or nitrogen. Now, hydrogen bonding, once again, in all intermolecular forces involve at least two molecules interacting with each other. So if we were to have two water molecules, our hydrogen bonding here would be this oxygen and hydrogen interacting with each other. And then next for, let's say, ammonia or NH3, if we have two molecules of NH3, then the nitrogen and hydrogen are interacting. And once again, this is just representing our hydrogen bond. So that has to be the case. And then what if we were to have two completely different molecules, like let's say water and ammonia? Well, that's also hydrogen bonding, since we can have that oxygen interact with that hydrogen, or even vice versa. We could have, I'll show that, we could also have this nitrogen interacting with this hydrogen. So that's a way of seeing how hydrogen bonding is going to play out. All right, so that's what I want you guys to pay attention to when we're looking at hydrogen bonding. It is really going to be important to know that it's for fluorine, oxygen, and nitrogen, not for any other atom like sulfur or chlorine, and nothing like that. All right, so then next, I'm going to get into dipole-dipole. So with a dipole-dipole or dipole-induced dipole, that's going to be talking about just polar molecules. So if the molecules that are interacting with each other are both polar, then we know that, yes, it is dipole-dipole. The fact that we're talking about, like, let's go over, like, what in the world a dipole moment or a dipole is. That dipole exists because a molecule is polar, meaning there's that unequal pool of electrons. So one atom wins that tug of war because one atom was more electronegative or was just stronger overall. So that's what I want you to think about when we're talking about a dipole or something being polar. So in this case, I know that the sulfur is going to be polar, once again, because there are lone pairs, right? There are lone pairs on this central atom. So I know this entire molecule is polar. It's a replica of itself, so I know that these two would interact. This is not hydrogen bonding because sulfur is not a part of hydrogen bonding. That's only fluorine, oxygen, and nitrogen. So I know, okay, this must be dipole-dipole. Moving on to the weakest one. So our weakest one is London dispersion. The reason why this is so weak is because it's on everything, basically. So anything that interacts with each other has some sort of force or has some sort of interaction, but it doesn't mean that that interaction is strong. So that's why we have something known as London dispersion, intermolecular forces or London dispersion forces. Then that tells us it has to be, everything can technically interact with each other, right? But it doesn't mean that that interaction is strong. So that's what I want you to think about. Now with this, you're going to see London dispersion mainly on nonpolar molecules. So if you have a nonpolar molecule, and a lot of times how the ones that I just instantly know are nonpolar are something called a hydrocarbon. So a hydrocarbon is when we just have carbon made up of some amount. So we don't know how many carbons, but there's some amount. And then hydrogen. So this is a hydrocarbon because we only have carbon and hydrogen in our molecule. That's what I mean by that. So since this is nonpolar, and I know this is nonpolar because it is symmetrical, there's an equal pool of electrons every single direction. So that equal pool of electrons, well, that cancels out. So then I know it has to be nonpolar. Okay. And then so there is technically still an interaction with, let me go back, an interaction with these two. However, it's just super weak. So just know that London dispersion is the weakest. Now let's go over arranging this, because this is what you're typically going to see on your exam, where you're going to be asked arrange these molecules in increasing order. All right. So arranging these molecules in increasing order, the first thing that you want to do is just draw the Lewis structure. So I'm not going to go over how to draw Lewis structures. I do have a video on that I can put in the chat right now. So I'll put how to draw Lewis structures. I have a separate video on that. It also talks about geometry, molecular, and the other geometry, electron. There we go, electron geometry. So I do have that if you still need help with Lewis structures. But for now, I'm just going to go ahead and draw the Lewis structures already. And then what I'm going to look at is I'm going to focus on what intermolecular forces does every single one of these have. And note that some of these molecules can have more than one intermolecular forces. So for the first one, that's CH4, we know that we said this has an equal pool of electrons, meaning everything is going to cancel out. If we had a tug of war with someone with equal amount of strength as ourselves, or if we literally had a clone and it was the same person doing that tug of war, then I know, okay, those are going to cancel out. No one's going to win. So that's how I know it's nonpolar. So then this must be London dispersion. And then for the next part, we saw that this one was polar because it has electrons on our central atom. So since I know this is polar, this must be, and I'm thinking of this, by the way, they're not going to give you two molecules. I've always found it strange that they don't, but this is how the question would actually be asked. And they're having you assume that you're going to be interacting with two of the same molecule. So like I'm going to have a duplicate of that H2S, or I'm going to have a duplicate of that CCl4. That's kind of how they word the question or ask the question. So just beware of that. That's why you don't see duplicates of this. So then now for this H2S, what I'm going to see is it's going to be dipole-dipole, but everything has London dispersion, so I know London dispersion. For the next one, this one once again is going to have an equal pool of electrons, meaning it's nonpolar. So since it's nonpolar, the only thing it can be is London dispersion. And this last one. So there are lone pairs, sure. But the main thing to focus on, if I were to have a duplicate of that NH3, then I know that it would be hydrogen bonding, because hydrogen bonding only occurs when there's a hydrogen bonded to either a fluorine, oxygen, or nitrogen of a different molecule, not within the same molecule. So I know that if I were to have a duplicate of this, which is what they want you to assume, then I know, okay, this hydrogen would then interact with the nitrogen of the other molecule, and yes, that would be characterized as hydrogen bonding. The next thing, is this polar? Well, yes, because there are lone pairs on our central atom, it does make it polar. So this is dipole-dipole, and of course, everything has London dispersion, meaning it's going to be London dispersion. Okay, so arranging something in increasing order, when we're talking about increasing order, that's going to be going from the lowest to the weakest to the strongest, right? Going from lowest to increasing order, we're going to keep on increasing. So I want to start off with, I'm actually going to start off with the strongest, the one that I personally know, and I'm going to put that at the end. So the one that has the most intermolecular forces, but specifically the one that has the strongest. So the one that has the strongest out of all of these four is going to be hydrogen bonding. So I know that has to win, plus it literally has everything else. So hydrogen bonding is going to be the strongest of them all. Then next, the second one that's going to follow is going to be the one with dipole-dipole, because that's the next one on the ladder. So I know H2S is going to be the next one. But we have two of the exact same intermolecular forces. Since they're both London dispersion, this is extremely important, guys. There is a tiebreaker. So your tiebreaker, whenever you have two molecules that are both London dispersion, is going to be the molar mass. The larger the molar mass, the stronger the intermolecular force. So that's going to be your deciding factor. So I'll repeat that again. It's going to be molar mass. So the larger the molar mass, the stronger the intermolecular force. So which one has the larger molar mass? Well, hydrogen only has a mass of really 1.01, while chlorine has a mass of 35.45. So right then and there, we can tell, all right, well, it has to be this one because there's so many chlorine and hydrogen has such a low molar mass. So I would actually do the entire molar mass of the molecule, though, just to let you know. But in this case, I could automatically tell, well, CCl4 has to be has to be it. And then the weakest one, because it has a smaller molar mass and only has London dispersion, will be CH4. All right, so that I know has to be the case, okay? So that's going to be if we're just looking at intermolecular forces and putting this in increasing order. I'm going to move on to the trends. So this is extremely important. Make sure to write this down, take a screenshot, something. And I say this because this is going to help you understand what trends and how everything relates to intermolecular forces. So let's say for the first one, if I were to be looking at boiling point, how that is either proportional or non-proportional to intermolecular forces, well, they're going to be the exact same. And I want you to think of it this way. Whenever I think about boiling point and intermolecular forces, I think about intermolecular forces are essentially talking about the strength between two molecules. And let's kind of say my hands are the two molecules. And they're going to join forces, right? They're going to connect. Now, the boiling point is essentially saying this. If this force is strong enough, it's going to take a higher boiling point, meaning it's going to take a lot more heat to break and separate these two molecules. But if this is a really weak force and this isn't, connected so much, maybe this is like London dispersion, then it's not going to take much of a boiling point or much heat to separate these two from each other. So that's how I remember it is, okay, if I'm trying to boil something and if the intermolecular forces are so strong, meaning they're so, bound together, then I know it's going to require more heat to separate it apart. So it's a higher boiling point. And vice versa. If it's really, really weak, then I know, then if it's just London dispersion, it's going to take a lot lower boiling point or heat to separate it. And then we can still think of the same sort of concept here with surface tension. The higher the intermolecular force, the higher the surface tension. Same goes with viscosity. Viscosity is really just how thick something is. So in this case, the higher the intermolecular force, then the more viscous or the thicker the solution is. And then lastly, this is the one that differs. So our vapor pressure, as it increases, our intermolecular force is the opposite. It's actually decreasing. So make sure to definitely know those. And of course, make sure to know just which force is stronger and what the order is in strength. So let's do maybe one more and then I'm going to move on to the next topic. So if we were to arrange this in increasing order of boiling points, remember that the trend says as we increase our intermolecular forces, our boiling point also increases, so they are proportional to one another. So the same thing would apply for this. It's going to be the exact same trend that we found before, order that we found before. And then next, if we were to have something else, like let's say vapor pressure, well, we stated that the higher the vapor pressure, the lower or the weaker the intermolecular force. So it would be the reverse or the opposite of it. So definitely know and understand that. I also recommend know what increasing order means. It means going from lowest to highest. Know what decreasing order means. It means the opposite, going from highest to lowest. So definitely understand that with these types of questions, sometimes they can be worded a little bit tricky. So these are just good multiple choice questions that I've seen. Okay. Now on to the next topic, which is talking about formal charges. And I just want to see how everyone's doing so far in the chat. I do see a lot of people are coming up. So everyone who's coming in, hello, welcome. And a lot of these videos, by the way, that I already have, which I think the live moderator has been putting different links in there. So definitely make sure to check out. I do have several different videos on gas laws. I do have a lot talking about gas stoichiometry. I even have notes that are for gas laws if you guys are struggling with that. So the gas law notes that I have, they cover how to use every single gas law. So including partial pressure, Dalton's law, combined gas law, ideal gas law. It has so many different examples. Plus it also has gas stoichiometry. Or if, let's say you have to find the density of a gas or molar mass of a gas, it includes everything I can possibly think of for gas laws. So make sure to check that out. I just put the link in the chat. So that's for gas laws. And then the next topic that I'm going to be going over is formal charges. This is actually part of what you're seeing right now. This is part of my notes already. So this is specifically of my Lewis structure notes. So if you guys are struggling with Lewis structures and would like additional help, I do have notes on that as well. So it covers everything from how to draw Lewis structures. It covers, formal charges, resonance, Vesper theory, geometry. It covers a lot. Hybridization. So like I said, it definitely includes everything you really need for that topic. Okay, so formal charges. This is going to be a great way to kind of think about this. Out of breath. Okay. So our formal charges, what I want you to think of them as, it's essentially just the charge of one individual element that is within the compound. So what I mean by that, if we wanted to find the formal charge of, let's say, sulfur, that would give us just the charge of sulfur within this entire compound. All right. So that's what I want you to think of formal charges. Now, the reason why formal charges are so necessary and so helpful is because it helps you see if you drew the correct Lewis structure. And that's why I personally really like formal charges, just because it has helped me avoid a lot of mistakes. If I drew a Lewis structure and I wasn't sure, is this the correct one? I can draw it this way. The formal charges are going to be the deciding factor as to which one is a better Lewis structure or the correct Lewis structure. And I'll show you how to do that. So in this case, there is a formula. So make sure to know your formula for formal charges. And that formula is this. So it's going to be our formal charge of whatever element we're looking for. And then we have the typical valence electrons. And then next, we're going to subtract that by the bonding electrons. So the electrons that are touching or right there in the bond. And like I said, we'll go over all this, don't worry. And then plus each individual lone pair. So let's do an example of this. Let's actually do the math. And let's start off with finding the formal charge of sulfur. So finding the formal charge of sulfur, so I'm going to put this here. The typical valence electrons for sulfur, and remember, if we're looking at valence electrons, I don't have it here, but let's say if we were looking in sulfur's here, hold on. So the noble gases are 8. I'm working my way down. The halogens are 7. Ran out of room. And then sulfur is somewhere here. And it's going to be 6. I ran out of room. Okay, it's going to be 6. But our valence electrons for sulfur are going to be 6 valence electrons. I'm going to subtract that by our, here's the really important part, guys. For our bonding electrons, what this refers to, it's only talking about that specific bond, but specifically what electron is touching that element or atom that we're looking for. So in this case, we know, sure, there are two electrons here in this one bond, because 2 electrons makes up one bond, but there's only one electron that is specifically directly touching that sulfur. So then that's when I know, okay, this has to be 1, right? So then that has to be 1, and then now I'm going to add this to each individual lone pair. So individual, here we have 2, 4, and 6. So each one, you literally count every single one. So 1, 2, 3, 4, 5, 6. And then next, I'm going to combine everything. So this is really 6 minus 7, so this is -1. So I know sulfur has a -1 charge. And then next, I'm going to see, okay, let's do the same thing for carbon. So for carbon, I would find the formal charge of carbon. The typical valence electrons for carbon is 4. I'm going to subtract this by however many electrons are bonded to that. So here we said there's 1. Here there's 1, 2, and 3, so a total of 4. There are no lone pairs on the central atom, so then this is 4 minus 4, so 0. The central atom is 0. Then lastly, I'll do the same thing for nitrogen. The typical valence electrons for nitrogen is 5. I'll subtract this by our bonding electrons. So here we have 1, 2, and 3. So we have 3 bonding electrons plus the individual lone pairs, so 1, 2. And this is 5 minus 5, that's also 0. And you'll notice that with your formal charges, if you were to add up all the formal charges of your elements, it will equal the overall charge of the entire molecule. or compound, okay? So that's what we're seeing here. So then that tells me, okay, this worked out, but is this the best structure? How I can tell this is the best structure, and we're going to go over two different types, one being a neutral compound and the second one being a charged compound. Well, sometimes we're going to have to look back at electronegativity. And remember with electronegativity, which I'll put over here, the trend increases as we go from left to right and as we move up a column. So really whatever is closest to fluorine is going to be the most electronegative because fluorine is our most electronegative atom. And then I'm just going to show here what our formal charges would have been. That's just the nicer version. But in this case, that's how we can find our formal charges. Let's get into how you can tell what formal charges you're going to want depending on the structure or depending on the charge, really. So let's say if we had something that was a neutral compound. The formal charge for this is we want all the elements to be 0. So we want all of our formal charges to be 0 for a neutral compound. That's going to be our happiest or best structure. And that's, of course, if it's possible to do so. So let's say if I had something like this, and then I really drew out the structure. Well, if I were to look at the formal charges, since that's what we went over, everything has a formal charge of 0 because this entire compound is neutral. It's 0. So since I can see that, I know, yep, this is the correct structure. And especially your central atom wants to be 0. It wants to have a formal charge of 0. That adds to the stability of the structure. So then now I know, okay, if I were to do these formal charges, my oxygen here, oxygen has 6 valence electrons. I'm going to subtract this by our bonding electrons. So our bonding electrons of that oxygen, there's 2 here, okay? And then that's how I got the 2. And then plus 4 individual electrons because here we have 2 and 4. And that gives me 0 since it's 6 minus 6. And then next for chlorine, note that they're all the same, right? They all have one single bond and they all have 1, 2, 3 lone pairs. So since they're all the same, we only have to find the formal charge of 1 chlorine because nothing changed. So I know chlorine has a formal charge of, valence electrons of 7, and then I'm going to subtract that by the bonding electron, which is just 1 on each one, right? So then I'm just going to get 1, and then plus 6 because there are 2, 4, and 6 electrons. That gives me 0. And then of course I'll do the same thing for phosphorus. I think you're getting the point by now. So for phosphorus, we have 5 valence electrons typically. I'm going to subtract that by the total amount of bonding electrons on phosphorus. So here we have 1, 2, 3, 4, and 5. So once again, bonding electrons are just the electrons found on the bond. And it's specifically the one, it's going to just be like 1 in a single bond that's directly touching that atom. All right, that's what I want you to think of it as. So that's where I get 5. There are no lone pairs. So this is happy. Okay, so now that we know that and we got a little idea of a neutral compound, we kind of already discussed something that was a charged compound. So if I were to have something like this, I really put everything in with our formal charges now that you have an idea of what to do. But if I were to draw this overall structure, well, we'll see that the central atom once again is 0 and it wants to be 0. Now, something else that you're going to notice for something that is charged is we want our most electronegative atoms to be negative. And let me actually go, even before I go back, I'll go back in a second. But note that we also see that all of our formal charges, if we added them together, would give us the overall charge of the compound, which in this case is true. And that's how we know, yep, check, that is correct. But if I were to go back to this structure, well, let me actually continue. Okay, so if I were to go back to this structure, we saw that the sulfur was the one with the negative, right? This is a negatively charged structure or a charged structure. So overall, now what I would look at is if this is the best structure or if it's correct, I know that the most electronegative atom is going to be negative. And which one is the most electronegative atom versus our sulfur or our nitrogen? Well, it's going to be sulfur. So in this case, So it's going to be sulfur. And then I know, okay, yes, then this would be the best suited one for this structure. All right, so that's how I can just instantly tell if the formal charges are correct. So once again, we want our most electronegative atom to be negative. If it isn't, then that isn't the correct structure. And then we want the central atom to be 0. So that's how you can just easily tell how, which formal charge is actually correct and which one isn't. So that being said, let's keep going because I do have more to talk about. I did get a quick question on Hund's rule. So what Hund's rule is, it's pretty much just talking about how electrons fill their orbitals. So how they're actually being filled. And let me show that. So let's say with something, I'll put it in blue. Let's say something like this. This is going back to like energy diagrams, or you guys might have seen this in molecular orbital diagrams. I'm just showing this on a typical thing that you would look at for electron configuration, where hydrogen has 2 electrons, right? So, or I'm sorry, hydrogen has 1 electron. If I were to just look at hydrogen, let me go back. The electron configuration is just 1s1, right? If I were to look at helium, that's just 1s2. Now, if I were to fill this orbital, well, and actually, let me not do that one. Let me do carbon. That one's better. Let's say if I were to look at the electron configuration of carbon, that would have been our 1s2, 2s2, and 2p12. Okay. And of course, if you guys need a refresher on electron configuration, I do have a video on that. So make sure to check that out as well. Okay, so if you need a refresher on how to do electron configuration. Now, how I'm going to look at this, Hund's rule is essentially saying this. You fill one orbital, like you fill each orbital, you give it 1 electron at a time. You don't fill the entire orbital and then move on. And I'll show what I mean. So let's say specifically, if I were just to start off with 2s2. Well, since there's only one subshell, there's only really 1 orbital there, I'm just going to fill this accordingly, and I filled that orbital. However, for our p orbitals, here we're going to see that we only have 2 electrons because it's 2p2. Now, I'm not going to do this. I'm not going to fill these 2 and then move on. That is not correct. Hund's rule is instead saying we want to fill each one, and that's it. But let's say if we had 2p6, all right, for something like that. Well, and let's say this is something different. Let's say this would be neon. Okay. If this were neon, then how I would fill this if this is 2p6, then I would just do 1, 2, 3. I'd come back around 4, 5, and 6. That's all Hund's rule is saying. I want you to think of electrons kind of like they don't like each other, really. They don't like each other. Electrons don't like each other because they repel from each other. So they don't like to be next to each other. So think of it as they would prefer to sit away from each other as far as possible. So that's why you want to fill your shells 1 at a time and then come back if there's nowhere else to sit, all right? If there's nowhere else to be. So that's what I want you to think of. All right, that's Hund's rule. Whew, all right, this next one. So this next part is specifically talking about lattice structures. This is more on if you are in high school, you most likely won't see this unless you're taking, I don't even think in AP you take this, but this is specifically for a college level general chemistry class. So just beware of that. So with this, when we're talking about lattice structures and unit cells, this has to do with like lattice energy. And what lattice energy is, what I want you to think of it, let's say we have 2 different gases. If we were to try to get these gases and press them down essentially and trying to like smush them down into some sort of crystal-like form or something like this, right? Like let's say we had like 2 different atoms here and I'm just pushing them down and trying to get this sort of cell. Lattice energy is the energy required to take those 2 gaseous states or 2 gases to bring them together to form some sort of lattice crystal. That's all lattice energy is. It's the energy required to take these gases to form that lattice crystal. So, and this is what I want you to think of with the lattice structures. So there's going to be 3 different types of unit cells or structures that you will absolutely need to know. This table that I'm showing right now, please know it. It's going to be a lifesaver. And this, once again, is still part of my free survival guide, my chemistry survival guide. So if you haven't already, make sure to check that out. It is in the description box along with other helpful resources. So now, what I want us to talk about before we get into every single type of structure is let's just look at how they're figuring out coordination numbers, how they're figuring out how many atoms are in the cell per se. So these are pretty funky images, I know. With this sort of concept, essentially what they're saying is it's kind of like they're taking this imaginary cube sort of type, and it's like they're kind of like cutting those atoms and seeing, all right, how much in total, even if we had like 1/8 of an atom and we added all that up, how much would this form? How many atoms would this actually be in the cell? So essentially, since every single one of these would be 1/8, we would multiply that by 8 of them, because if I were to look at this cube, there actually are 8 of them, right? We have 2, 4, 6, and 8. Well, in this case, I know there's only going to be essentially 1 atom in that unit cell. And this is just how they're getting those numbers. And then now with our coordination number of 6, this is once again just saying kind of where this falls into our simplic cubic cell. Now, I don't want you necessarily to worry too much as to how we found that. Typically, you're just tested on knowing that it is found. You're not being tested on how it's derived, luckily. So that's why I don't want you to worry too much of how everything is necessarily found. You're not going to have to draw this. Goodness, I wouldn't be able to draw this. But looking at the next one, our body-centered cubic is telling us that there is going to be 1 atom already in the cell. And then from then out, we're going to see, okay, once again, we have different atoms along the edges or the corners. And then from there, once again, we're just going to do that math. We're going to see that there's 1/8 at 8 corners. So then that's when I know 1/8 times 8 gives us 1. And then we're going to add 1 because there's 1 atom in the center. So then from there, I know, okay, 2 atoms. And then the same thing goes for our face-centered cubic. There I know, okay, how many atoms are going to be in my cell? Well, here we have several different types. Once again, I don't want you guys to worry too much about what this looks like per se. I just really care that you guys know how many atoms are in the cell. It would be 4, just because we would take half of 6 different faces, because there's 1, 2, 3, 4, 5, 6 inside. And then from there, I'd multiply that by 6. So half of 6 gives us 3. And then once again, 1/8 of the 8 corners along the edges. If this is just looking like nonsense, don't worry too much about it. What I really want you to focus on and know is this table. Okay, so focus on this table. This already tells you how many atoms, what the formula is, and what it's going to be. So for a simple cubic cell, what I want you to know that there's going to be only 1 atom per cell. And then next, this is known as our edge length. So our edge length is really just referring literally to our edge length here. So this is going to be our L is equal to 2R. That's something to know. And then for our body-centered cubic cell, that's going to have 2 cells inside, or overall. And then next, this is going, or 2 atoms overall. And then this next one is going to have a formula, the edge length again, is going to have a formula of L is equal to 4R divided by the cube root of 3. Last one is going to be our face-centered cubic cell, where we have 4 atoms per cell. And then here, I know we have a little bit of a different formula here, where we have our edge length is equal to 2R times the square root of 2. So all of these, please make sure to know. All right, so make sure to know all of these formulas as well as which one goes along with each. Because what they're going to say in an example, and we're about to do an example, is they're going to tell you what type of cell it is. But the fact that they say what cell it is, you instantly can tell, oh, if I know it's a simple cubic cell, then I know that there's 1 atom, and I know the edge length is going to be this formula. All right, so that's what's going to be really beneficial. So let's do a question. So this one's going to be finding the molar mass. Let's say if we had something like this, where we have a metal crystallizes in a face-centered cubic structure. So right then and there, it tells us what it is. So that's going to give us a lot of information already, like the formulas that we're going to use. And then it also says it has a density of 11.9 grams per cubic centimeter. If the radius of the metal is 138 picometers, what is the molar mass of the metal? So I know, okay, well, here, the molar mass of the metal, that's what we're trying to find with all this given information. So there are a series of steps that we're going to have to take to get to that, all right? So first things first, we identify what the face-centered cubic cell is, meaning how many atoms per cell are there. Also, what is our edge length? So from that chart that we talked about earlier, well, this is going to be extremely beneficial because it's going to help us know what formula we're going to need to use. So since we're looking for the molar mass, the fact that they gave us the density is going to be our biggest clue. All right, so our game plan here is going to be going from the radius that was initially given. So I know R already. I know R is 138 picometers. However, this is in centimeters, right? So I don't want picometers. I want to convert that. So that's going to be my first step, is to just convert picometers to centimeters using the metric system. And then remember that we can't just jump instantly from picometer to centimeter. There has to be something in between. So our meters is going to be that kind of center one that we're going to have to do. So then I'm going to set that up. And then setting this up, I'm going to start off with my radius. I'm just converting that radius. So 138 picometers per every 1 picometer, there's 10 to the negative 12 meters. That would cancel out. Now we're at meters. And then I know that there's for every 1 centimeter, there's 10 to the negative second meters. And that would cancel out. And then now this gives me this amount of centimeters. So now that we have the correct centimeters, what I'm going to do next is I'm going to find what L is, all right, because I know what R is. So this is our formula that we're going to be using, and that was just the fact. I knew this just because they told me it's a face-centered cubic structure. So now, since I know what R is, and it is in the correct unit, this is our R, I'm just going to plug that in. So just plugging that in. So I'm plugging in the R here. It's going to be 2 times this value, and then times our square root of 2. That's going to give us this value. So now I know what L is, which is great. But remember, I'm looking for my mass. And what's going to allow us to get to our mass is the fact that this is in grams. The density is in grams. So since I have centimeters right now, what I need to do is I need to find the volume. Because remember, density is mass divided by volume. So what I have to do is I actually have to cube the edge length, or the L, to find our volume. So when I do that, now I have the proper unit. So now I have the proper unit of cubic centimeters. And then next, what I'm going to continue doing is, since I have the volume, now I can plug that into the density formula and find the mass. So I know what the density is, right? We were given that. And I'm just going to plug everything in that I know. So this is what I found for the volume. This is what we were initially given for our density. And then from there, I'm just going to multiply both sides by this value. And then from there, once I do that, the centimeters and centimeters, the cubic centimeters would cancel, and we would be left with our grams. So the other thing that we have to continue doing is, since we're looking for not just the mass, we're looking for the molar mass. Remember that molar mass, its units are grams per mole. So we found the grams. We found what's on top. So check, that's out of the way. Next, we have to find how many moles are in this face-centered cube or cubic structure. So what I know is, well, there's 4 atoms, right? That's where this is going to come in. The fact that I know there are 4 atoms, well, atoms goes with what? Avogadro's number. So Avogadro's number, I'm going to place that here so they can line up and then cancel per every 1 mole, because I'm trying to get to moles. So how I knew to do this was because, 1, I wanted the molar mass. We stated that molar mass was grams divided by moles. I needed moles now. So what allows me to get to moles? Well, I know I have to connect somehow atoms to moles. The connecting factor, or the conversion factor that allows us to go from atoms to moles, is then Avogadro's number. So then that's how I know to divide that and then get the moles. Last step is just to divide those two together to divide our grams and our moles, and we get our molar mass of the metal. So I know these questions do tend to be long, but like I said, if you know that table that we talked about initially, then that's going to help you a lot because it already gives you the formula to pretty much start off with. And then just as a note, you're typically always or almost always going to be given this in a different unit, the radius in a different unit, either picometers or something else. I typically see picometers, but you're most likely going to have to convert that like right in the beginning. So beware of that. How I knew to convert it was just the fact that the density was in centimeters and not in picometers. So that being said, that was the main thing that we were looking at. I'm seeing let me see how everyone else is doing. Perfect. I think everyone had some different questions that they were asking. Make sure to check out a lot of the videos that I have because I now have almost pretty much a complete summary of what you guys need. I've added a lot more videos. Even some of my past lives, I went over a lot of different topics that I hadn't before. So whether it be I had some talking about, enthalpy and enthalpy of formation, standard enthalpy of formation, I do have a video on that. So several different things. So make sure to check out the videos that I already have. And then if Bobby, if you didn't cover lattice structures this semester, don't worry about it. So it is dependent on really the curriculum. Sometimes I do see this is more for a general chemistry class in college. That's when I personally took it or when I've seen my students use it. So don't worry about that. If you haven't covered it, be thankful. So now this is the last live of the year. Goodness. For everyone who even is joining today or has been here through multiple lives, thank you so much for being here. I enjoy doing these lives and I enjoy teaching you guys. That's always it's a fun thing to do. So make sure to check out the other videos that I will have coming up. And if I have helped you in any way this semester and you would like to help me, support me and in this channel, by all means, I would love that and I would really appreciate that. I do have a Patreon page that I finally created. So if you would like to support me with my Patreon page, I just put it in the chat. It's also in the description box of this video. So like I said, if you feel that that's what you would like to do, by all means. And of course, if not, I completely understand. So thank you so much, seriously, guys, for all being here. Another thing I wanted to mention was if you have any more, if you need any more help, whether it be with chemistry or if you're continuing on with chemistry or if you're just taking other math classes, physics classes, biology classes, all the classes. And if you still need additional help, I know that I don't technically teach that, but I do recommend a source called Chegg Study. That personally helped me with a lot of different topics and a lot of different classes that I was struggling in. So especially it helped me understand my homework, which is essential because those were practice problems. So it was really nice to try that out and see where I went wrong and what I need to improve on. So Chegg Study is just a great way to see where you need to improve on because it does give you that step-by-step solution. So you can see, oh, I forgot that step. I need to do that next time. So I personally really liked that. So awesome, guys. Thank you so much for being here. And I hope you guys have an awesome week. Kill it on your finals, guys. Like, push yourselves. I know you can do this. And I have plenty of videos for you guys to binge watch on if you need them. And of course, as mentioned, if you do need additional help, there are links in the description for that. And there's also notes that are currently on sale, 40% off all my notes. That's ending today. So that is the finals sale. So make sure to check that out if you do need additional help and want to cut your studying time in half because I know it's game time now. All right, guys. So everyone's saying thank you. You're welcome. Oh, and I forgot to mention, for everyone who is taking, Brittany just reminded me, that they'll be taking OChem next year. Perfect. I do have a second channel. So a lot of people don't know, but I do have a second channel on organic chemistry. So if you're continuing on or eventually going to continue on to organic chemistry, I have you covered. So don't worry about that. I will be covering, or I have several videos on, someone just put a naming question. I do have several videos on organic chemistry. I am adding more. And I do have how to name alkanes, which this is going to help the person that just put a naming there. So I do have, or actually that one's an alkene. But I do have several videos on that, so make sure to check that out. And yeah, so thank you so much once again for being here. Have an awesome week, and I hope to see you either next semester, or if not, good luck, guys, with everything that you decide to do. All right, guys. See ya.